Hello guys, welcome to my YouTube channel. So in this video, we're going to talk about the mobilization of fats, right? So the mobilization of fats just describes the mechanisms or the steps we're going to go through to break down the fats that are stored in various parts or tissues of the body. So examples of the tissues that store fats are like the adipose tissue, and now we're just going to zoom into one, that's the adipocyte, that is the cell in the adipose tissue. So fats are always stored in various forms, and the one that we are going to talk of today is just the triglycerides. We are going to see how we are going to break down the triglycerides into its various components, and how we are going to manipulate those components to yield energy. And we're also going to talk about why are we breaking down fats. Of course, you know that the body normally depends on carbohydrates as the main or the primary source of energy. But now, what situation can make us mobilize fats, break down fats? And of course, you know that fats will always has a lot of energy, yeah, but normally they are not being used. So we're also going to describe why are we using fats, or why are we using carbohydrates more than fats. Now, let us get started. So when does the mobilization of fats begin or happen? Now, the mobilization of fats or the breakdown of fats occurs during the fasting state. During the fasting state. So the fasting state means that the blood glucose level is low. So low glucose level. So when the blood glucose level is low, and of course you know the body needs the glucose and the energy to run a series of physiological functions. So the body is going to divert from carbohydrates into fats, right? So we are going to see when are we like actually breaking down these triglycerides, because we said it's the fasting state. Now, how are we going to start? So we are going to start this way, right? During the fasting state, or when there's low blood glucose level, of course, you know we always involve the insulin, the glucagon to regulate the blood sugar level. But now in this case, when there's low blood sugar level, then you're going to stimulate the isolates of Langerhans. Isolates of Langerhans are just like clusters of endocrine system that are located in the pancreas. Now you can look them here. These are the isolates of Langerhans. Now they are different. They contain different cells. You have the alpha cells, you have the beta cells, and you have the delta cells. Now, in this case, when there's low blood sugar level, we are going to stimulate the alpha cells. Now, the alpha cells are going to release a molecule of glucagon. Now, glucagon is a hormone. We're going to release glucagon hormone. You know the role of glucagon hormone is always to raise the blood sugar level back to normal when there is a decrease in blood sugar level. Now, the easy way to master that is like glucose is gone. So, glucagon. Now, that is very easy to master. Now, insulin, we are not going to talk about that because it is when there is high blood sugar level and need to return it back to normal. Alright. Now, another situation is when, you know, during stressful situations, acute stress, we can involve the sympathetic nervous system. Now, sympathetic nervous system, sympathetic nervous system is going to stimulate the adrenal medulla. Now, sympathetic nervous system has postganglionic mononeurons, actually located within the lateral great horn of the spinal cord. Now, they're going to stimulate the adrenal medulla, and the adrenal medulla has the postganglionic mononeurons in form of chromaffin cells that are going to stimulate the release of certain hormones. So let's see here. We're going to stimulate the adrenal medulla, then we're going to release two hormones. That is the epinephrine, and that's going to be produced in large amounts, about 80% of epinephrine. 80%. Then you're also going to produce trace amounts of norepinephrine. About 20%. Of course, we can produce many other hormones like cortisol, we can produce growth hormone, we can produce thyroid hormones, which can have the same effect, but we're just going to focus on these the three main hormones that are going to be involved in the mobilization of fats. Now, either of these hormones can now come and bind to this particular receptor here. Now, what's the name of this receptor? This receptor has a pretty cool name. It's going to come and bind there. So either of these hormones, either glucagon, epinephrine, or epinephrine, can come and bind to this G protein coupled receptor. Now, G protein coupled receptor is going to associate itself with a protein located inside the cytosol. Let me just draw it this way, that way. You know, the protein that the G protein coupled receptor is going to associate with is a heterotrimetric G protein. Heterotrimeric means it has 3 subunits. We have the alpha subunit, the beta subunit, and the gamma subunit. Right. Now it has those 3 subunits. But now in this case, it's going to be a stimulatory G protein. You know, you have 2 types of G protein. You have stimulatory and inhibitory. So this is going to be a stimulatory G protein. So when either of these hormones bind to the G protein coupled receptor, it's going to activate, leading to conformational changes. Then it in turn activate the stimulatory G protein. Then of course we know the dissociation of the alpha subunit, all those. So what's going to happen immediately is that the alpha subunit is going to replace GDP to form GTP. Now when it now converts GDP to GTP, it becomes activated, right? So when it becomes activated, it's going to dissociate from the beta and gamma. So when it dissociates, it's going to activate a molecule called adenylate cyclase. It's just a molecule located here. Adenylate cyclase. So when it activates adenylate cyclase is going to do what? It's going to convert ATP. It's going to convert ATP into cyclic AMP. Right. Now, what cyclic AMP is going to do is just going to convert a phosphorylated protein kinase A. So you're going to have protein kinase A. You're going to be phosphorylated protein kinase A. And why do we need all this? Now we need all this just to help us know how we are going to initiate the mobilization of fats. The protein kinase A, of course, you know it is a kinase, it's a phosphorylator. It's going to phosphorylate. Now, here there is a particular molecule. This molecule here is called perilipin. Perilipin. And right adjacent to it is a molecule of CGI. This is CGI. Alright. Now, what protein kinase A is going to do is going to phosphorylate. It's going to add phosphate groups onto perilipin. So, it's going to phosphorylate perilipin. Now, when it phosphorylates perilipin, it's going to activate perilipin. Now, when it activates perilipin, perilipin is going to become activated. That means a different kind. It's going to become activated. When it becomes activated, this leads to disassociation of the CGI. Now CGI is going to disassociate from the association. Then, when it disassociates, it's going to come along this way, right? So that's a molecule of CGI. It's going to come and bind to this molecule here, right? That's now CGI. And you know, this molecule looks pretty cool. It looks like a scissor, you know. And what's the role of a scissor? It's to cut. Now, this molecule here is going to cut something, but first of all, let us see. When CGI binds on this receptor, it's going to activate kind of something. Then once it is activated, now inside this adipocyte, we have triglycerides. Just as I told you, first are stored in the form of triglycerides. Now triglyceride, of course, you know, has a glycerol backbone and 3 fatty acid chains. Alright, now what is going to happen that this particular enzyme is going to cut the ester bond linking the fatty acid and the glycerol. So it's going to cut here. Alright, it's going to cut that ester bond. Now what is going to happen? We are going to release the free fatty acid. So we are going to release the free fatty acid. This is the first free fatty acid. Now, what is the name of this particular enzyme? This enzyme has a pretty cool name. It's going to be called adipocyte triglyceride lipase. Adipocyte triglyceride lipase is going to cut that ester bond, releasing the first free fatty acid. Then a molecule of CGI still comes along. It's going to again come and bind onto this another enzyme. Now what this enzyme is going to do is going to cut the second ester bond. Now let us see. This is a glycerol, then the fatty acid chain. Right? Now, what we cut here was initially the triglyceride. So this is a triglyceride. Or triacyl glyceride. Right? You can either call it triglyceride or triacyl glyceride. Now, what we have here is diglyceride or diacyl glyceride. and it's called it diacylglyceride. Now, what this enzyme is going to do is going to cut the second ester bond. Sorry, we're going to cut the second ester bond. So it's going to cut here. Right. Releasing what? Releasing the second free fatty acid. So you're going to have the free fatty acid, the second one. Now, what's the name of this enzyme? Guys, this enzyme is called hormone sensitive lipase. Hormone sensitive lipase. Right. It's going to cut the second ester bond, linking the fatty acid and the glycerol, releasing the second free fatty acid, and we are going to be left with a monoglyceride or monoacyl glyceride. Now, what we have here is a monoglyceride. Alright. Now, monoglyceride is going to be cut. Now, you know CDI still is going to come this way, then bind onto these are the enzyme. Then it's going to initiate the cutting and do it this way, so that you can see it that way. It's going to cut the last ester bond in the monoglyceride. Now, what are we going to form? We are going to form free fatty acid, the third free fatty acid. Now, we are also going to release what? A molecule of glycerol. So we have molecule of glycerol. Alright, now, what's the name of this enzyme? Guys, this enzyme is called monoglyceride lipase. Monoglyceride lipase is going to cut the last ester bond between this enzyme here. This molecule here is called monoglyceride or monoacyl glyceride. Now, guys, we have done the mobilization. We have broken down the triglyceride into its individual components. We have the three fatty acids and a molecule of glycerol. Now, I want to see where we are going to take these components of triglyceride. Now, you know glycerol has some hydroxide functional groups. Yeah, so it means it has some. It's like this kind of a polar. So we are going to have it here. So here we're going to have our glycerol. Let's just draw those three fatty acids and glycerol. Now they're going to be taken into the bloodstream, right? So glycerol is polar. It's just going to be taken to the bloodstream and transported to various parts of the body. Thereby, it can be converted to DHAP, that is a component of the glycolytic pathway, dihydroxyacetone phosphate. So it can be converted to dihydroxyacetone phosphate and move to the glycolytic pathway, leads to acetyl-CoA, then TCA, ETC, yield energy in form of ATP. Then the fatty acids, you know, they are not polar. So they are going to be transported in a form by the help of a particular protein. And this protein is pretty cool now. See this. There is a pretty cool protein. It's called what? It's called albumin. Now, albumin is going to package these fatty acids. It's going to package, let me just draw them that way. We're going to package these fatty acids and transport them to various tissues in the body. An example of tissues where they can be transported are like the skeletal, the cardiac, and even the liver. And the liver is very crucial because you can synthesize the ketone bodies, and we are going to see that later. So that is how we are going to transport those particular components of the triglyceride. But now, let us see this. Just as we said, you can transport the fatty acids into this is skeletal muscle. Now, what's going to happen? We're going to manipulate it and yield ATP. That's pretty cool. Alright. Now, some of these fatty acids can also be transported to the liver, and you're going to use ATP. Right. I'm going to use ATP. Alright. Then I said this glycerol can either transport it to various cells, then used you can phosphorylate this glycerol to glycerol phosphate, convert it into dihydroxyacetone phosphate, then you can go through the glycolytic pathway. However, some of it can also be transported. Now look at this. can be transported to the liver. Now, what's going to happen? We are going to undergo a process of gluconeogenesis. Gluconeogenesis. Now, this is just the synthesis of new glucose, right? Now, what are we going to get, guys? When we undergo gluconeogenesis, we are going to get glucose. We are going to form glucose. Alright, so I'm going to take glycerol, gluconeogenesis in the liver, then convert to glucose. But guys, remember what was happening, what was the main thing that drive this particular process, that the mobilization of fats, was fasting, low blood glucose level. But now see, we have a remedy, we have solved the problem. We have generated glucose through gluconeogenesis. Then this glucose can now get into the bloodstream. When it gets to the bloodstream, it's going to return back blood glucose level to normal. So we're going to increase glucose level is going to increase in the bloodstream. Right, and that's pretty cool. You see, we are in fasting stage. We don't have enough of carbohydrates, but now we synthesize glucose, gluconeogenesis, and everything. And now, guys, in our next video, we are going to see how specifically we are going to generate the energy through beta oxidation. We are going to break down these fatty acids through beta oxidation and see exactly what's going to happen so that we can get this energy in form of ATP. And I think that's all for this video, guys. If you found this video helpful, please make sure to subscribe to my YouTube channel, hit that like button, and please comment. Thank you very much. Let's meet in our next video.